So I'm Bruno I have a postdoc position now at the University of São Paulo. I'm going to present you a recent result that I have about birational equivalent Landau Ginzburg models. I will start thanking Alexander for the invitation. So the plan of the talk is to introduce two potentials, a toric potential and a Lie potential. And I finish with a result about birational equivalence of algebraic models, which will relate both potentials. So just start by stating what the Landau Ginzburg model means in this talk. It is for me a pair formed by a variety x and a holomorphic function from the variety to CRP1, which we call superpotential, or we'll just say potential most of the time. We'll also consider deformations of varieties in the potential to form what we call deformations of algebraic models. And at the end, we'll compare a deformation which and compare the property of duality about the variety and its deformation. As an example, there's a especially well-behaved class of algebraic models, which are called Lefschetz fibrations. So, from a topological viewpoint, a topological Lefschetz fibration in a complex variety is a pair of the variety and a function from the variety to CRP1 that has finitely many critical points of Morse type. So around each critical point, the function can be expressed as a sum of squares. Or from a symplectic viewpoint, a Lefschetz fibration on a symplectic manifold is such that for every regular value P, its pre-image is a symplectic submanifold of Y. Donaldson proved that every symplectic form manifold has the structure of a Lefschetz pencil, and a topological Lefschetz fibration can be obtained from blowing up the base locus of a pencil. So this is an illustration where we blow up the two red points. So here now we consider taking a complex semisimple Lie group. I will call frac G its Lie algebra. And if you take a Cartan subalgebra, frac H, we can have by taking the Hermitian form, H and G, we can have a symplectic form on the Lie algebra, as is expressed here, like the imaginary part of the Hermitian form. And now we'll consider, so this form is a symplectic form on this set, which is the adjoint orbit. It's the orbit of an element of in the Cartan subalgebra by the adjoint operator. So if we take this element on which we take the adjoint orbit to be the matrix whose diagonal elements are n, -1, -1, -1, and in the Lie algebra SL n plus 1, we'll call it a minimal adjoint orbit. This minimal adjoint orbit is diffeomorphic to the cotangent bundle of the projective space Pn. It is also non-toric Calabi-Yau manifold. So here's a result from Gasparin, Grama, San Martin, where if you choose an element on the matrix on the Cartan subalgebra, with H being a regular element, Then the height function defined in the adjoint orbit of H0, defined like this, is the fh of x is the Herten-Kelling form of x in agent x, has a finite number of isolated singularities, and thus defines a symplectic Lefschetz vibration. So in the case of the minimal orbit in SL m+1, this orbit is diffeomorphic to the cotangent of Pn, and this potential has n+1 critical points. So in the neighborhood of H0, which is this diagonal matrix on the left, we can express the height function as this equation on the bottom. So around H0, in a neighborhood around H0, we can set we can parameterize elements around H0 with two matrices x and y, and we can have an expression like that. The height function is like this expression here, where n is this n, right? This is the trace of the product of agent and H0. Each coefficient is a product of x is coordinates of this matrix x and y here. The y's are coordinates of the matrix y. And these are the eigenvalues of this matrix H. So this is a degree 2 polynomial. So this expression, which is the expression of fh written on a chart around H0, this is what we'll call Lie potential on the minimal orbit. So here agent and H0 are fixed, and this actually when I say fh of H0, it's actually around in a neighborhood around H0, right? And I can express any element like this. So this will be what we call Lie potential. Here's some facts regarding homological mirror symmetry for the adjoint orbit of O1. So by choosing H and H0 to be this matrix with diagonals 1 and -1, so the minimal orbit is the set of matrices with eigenvalues 1 and -1. O1 is a submanifold of SL2 of real dimension 4. The YL group is ±1. And therefore, the potential has two singularities, which are ±H0. So Saint-Martin computed the Fukaya category for this Landau Ginzburg model, which is this. And also Bailey-Meyer, Gasparin, Graham, Saint-Martin drove that LD2 and the LG model LD2, and also it's the compactified model LD2, both have no projective mirrors, which means that for any projective variety, the Fukaya category of LD2 is different from the derived category of the bounded derived category of coherent sheaves. Now we'll see what I mean by toric potential. If we start with Hamiltonian toric action of the torus on TPN expressed in this open chart. So here, what I mean by x0 I mean here that by xy I mean the coordinates on the base Pn, right? So around chart x0 different than 0, I can have this action. And from this action, we can obtain a Hamiltonian vector field given by this. And this induces together with the canonical symplectic form on the cotangent of Pn, it induces the potential given by this, the sum of -2i. Here I is the index of the sum, right? Not the imaginary number. -2i xy plus a constant c. So for hc we have a potential. And this is what we'll call the toric potential on the cotangent of Pn. So for toric Landau-Ginzburg models, we have some linear data associated to them. And this data allows us to have a recipe for obtaining dual models. So we have a diff, which encodes the divisor of the character to divisor map, and mon, which describes infinitesimal action on monomials. So the way that we do to obtain dual models is just gathering the div and mon information from the data from the Landau-Ginzburg models and just setting this data of the dual to be the reverse, right? So the mon of the dual is div of the original, and the div of the dual is the mon of the original. Here we have an example. So we'll take the LG model to be the cotangent of P1, and this potential given by x plus y squared over x. So this model is due to itself. And just to check this, is this they have the same toric data. Both mon and div are the same. And here we have an illustration. So here we can show how to obtain mon and div matrices. So mon comes from the the potential. So the powers of the potential induces the row of the mon matrix. So here x to the 1 induces the row 1, 0. Y induces the row 0, 1. And here we can see it's x to the -1 times y squared, which induces the row -1, 2. As for the mon matrix, we obtain them by taking the inward normals of the moment polytope. So 1, 0, which is this vector, 0, 1 to this horizontal segment, and -1, 2, which is the inward normal to this diagonal segment. So basically, also taking this recipe, we can take a toric variety and choose a potential so that it is self-dual. Here's another example of duality. This is a non-trivial, as in meaning a model that's not dual to itself, or the Landau-Ginzburg models are not equivalent. So this example is built using the recipe for building dual Landau-Ginzburg models, where I chose two varieties, and which have this div matrices, and I chose the potentials to be defined as in the with the data from the corresponding div, right? I chose F to have a potential given by div of Y, and a potential of Y given by the div matrix of X. So you can see this is P1 by P1, which have 1, 0, 0, 1, 0, minus 1, 0. That's right. This is div, and this is P2, right? So now we'll talk about what I mean by a deformation of Landau-Ginzburg models. And by deformation of Landau-Ginzburg models, I just made a smooth family of LG models with a parameter in an open set of Cn, which I'll just choose that this open set contains 0, so that I can easily say that in the 0 parameter, it is the original Landau-Ginzburg model, and when it's not 0, we call it a deformation, right? So we have a family of both varieties and potentials. And we'll use this squiggly arrow to denote that a model deforms to another one. So here we have a first example of deformation. I'll choose LG0 to be the cotangent of P1 with this potential. This is the self-dual example we saw earlier. And LG1 to be the cotangent of P1 with potential Qx. Where here we'll choose, these are both defined on the open chart where the first coordinate is not 0. So we'll build this family of potentials. And the family of varieties is constant cotangent of P1. So with this family, we obtain the deformation that takes LG0 to LG1. So our next objective will now describe a new family that takes the model with variety cotangent of P1 to the minimal orbit O1. So for this, we'll use the deformation of Hirzebruch surfaces. We have that the Hirzebruch F2 deforms to Hirzebruch F0, right? And this deformation induces the deformation of manifolds cotangent of P1 to the minimal orbit O1. So having the deformation, knowing this deformation of manifolds, which induces this deformation, we can have a deformation of varieties. And then we set these potentials to be the same throughout this family. So to recap the first example, here we deform Landau-Ginzburg models in a way that the underlying variety of the model is constant, and we change the potential. On this second example, we deform only the variety, and the potential is constant. So now we can combine the deformations to build a larger family, which then deforms the first model LG0 to the last one LG2. So here we now have a third deformation, which then changes both the underlying variety and the potential. So now we'll compare the lip potential and the toric potential. So we'll choose the same open chart here on cotangent of Pn, where we have defined two potentials, right? The toric and the lip potential. And we'll see now, which is my result, that for each n, we can find matrices H and H0 in the algebra SL n plus 1, and a constant C such that the lip potential and the minimal adjoint orbit ON, the lip potential on the minimal adjoint orbit ON and the toric potential of the cotangent bundle coincide on dense open charts. So the way we prove the theorem is explicitly finding H0 and C. So H0 is the matrix n minus 1 minus 1 minus 1, which means that potential is defined on the minimal orbit. And the choice of H means this, which we have different types of matrices depending if n is even or odd. And the choice of C is minus n squared minus n. So if we proceed with the computations of the potentials, this is the lip potential. So the way we chose the matrix H and H0. So we chose H0 so that it is we work on the minimal orbit. And the choice of H, where that, so we have this relation. So that we have the choose here, the right 2 times I here. And the choice of C is that, so on the toric potential, the C equals the trace of this product of matrices. So I wish now to restate my theorem and different wording. So I will call Landau-Ginzburg models to be called birationally equivalent. If their domains are birationally equivalent, varieties, and also their potentials coincide on Zariski open sets. So we can now restate the theorem like this: for each n, there exist matrices H, H0, and in the Lie algebra SL n plus 1, and a constant C, such that the Landau-Ginzburg models of the minimal orbit and the cotangent of Pn are birationally equivalent. And the proof is noting that we have this equality on the potentials for these choices of matrices and constant. They are equal on the Zariski open set given by this chart, right? V0. As a last statement, we'll check now how duality, an example of how duality behaves under deformation. So I'll take this Landau-Ginzburg model on cotangent of P1, this family of potentials, and then the family that takes LG0 with which sorry, the potential starts here and ends here, which has this toric data, and the potential on TP1, on the cotangent of P1, given by this expression, is the self-dual example. So we have, this is not a self-dual, right? Because we have different matrices for diff and norm. And then we see here that the information may take a self-dual Landau-Ginzburg model to another one, which is very far from self-dual.